people here do mobile spotting? All right, not too many, but it's still worth going through mobile spotting procedures. I know that a lot of people don't, so I won't dwell on it too much, but the questions that are on the test, I'll try and cover those better. Okay, this is an exercise in which you basically tell me what you would see from a given location. Here we have a classic supercell thunderstorm. It's got the hook echo circled in yellow. We've got the gust front forward flank downdraft with that white dotted line. And then each of the numbers there, 1, 2, 3, and 4, each one of those is a spotter position. And I'm going to show you a picture, and then you tell me which position you're at. Okay, here's the first picture. This is you just tell me where you're at here. This is what you see. Are you at 1, 2, 3, or 4? 2. Yes, you're at 2 because you're looking at that hook, but you're looking at the outside of the hook, so you cannot see the tornado. Okay, next one. This is what you see. Are you at 1, 2, 3, or 4?
3.
Well, actually, you're at number 1 because you're not able to see the wall cloud. If you're at 3, you could probably see the hook echo, the tornadic activity. In this case, you're looking more at just the downdraft area. Okay. Well, it's definitely either 3 or 4. Those are the 2 left. In this case, the tornado is far enough away that you're actually at number 3. You may be looking north or northwest with an unobstructed view of the tornado. Now, this is probably the best location to be in relative to the storm to see the tornado. You don't want to be real close to it, and you don't want to be in the way of it. However, keep in mind that supercell thunderstorms can often turn to the right of the mean wind. So if that was a right-moving thunderstorm, then you would become in the path of it. But if it was moving toward the east or northeast, then you're in a very good spot. Okay, now where do you see that? Okay, so you're too close. Definitely the most dangerous. This is sometimes called the bear's cage by storm chasers, and this is an area you don't really want to be in. So avoid that. Okay, what is this cloud feature? This is something that you probably saw a lot of in basic spotter training. It's a shelf cloud. It's approaching your location, so what would you expect? Would you expect the wind to be at your back because you're looking at a wall cloud? Well, we've already said it's not a wall cloud. Well, correct answer is C, wind at your face because you're looking at a shelf cloud. Now, the wind might not yet be at your face because the shelf cloud hasn't passed yet, but it will soon be. Okay, is this a tornado? Well, no, it's not. In situations where you have low light, poor contrast, you could make a rush judgment on this cloud. But if you look at it close enough and long enough, you will see it's not. Okay, what is this cloud feature here? It's not making contact with the ground and not rotating. It was just scud clouds. Basically what is sometimes called the scud bomb. It's basically just a harmless cloud. Okay, what is this feature? That's pretty much a textbook wall cloud. Okay, is this a tornado? You have a small debris cloud right near the base of it. You do have a condensation funnel, and it is rotating. So yes, you do have a tornado in that specific example. Okay, what about this feature? And this kind of goes back to your basic spotter training. We showed this picture in the basic. That is basically a descending rain shaft. That's when we talk about microbursts and basic training, we either show this exact picture or we show one very similar to it. It's a descending rain shaft. It's a pocket of cool air associated with the rain, and it's going to hit the ground and spread out, so it could be a microburst when it hits the ground. But you would not see any rotation with this. Does anything worry you about this image? Well, first of all, what do you see in this image? What kind of cloud? And then, what do you see on the ground? Yeah, you see blowing dust on the ground, and that cloud is actually a shelf cloud. That's not a textbook photo of a shelf cloud, but if you look at the front of it, right here, you see it is kind of an arc or a shelf. So it's not the angle that you're used to seeing a shelf cloud from. It's kind of a lateral side view of a shelf cloud. Normally when you see a photo of a shelf cloud, it's like a view from in front of it. So what you've got is strong winds behind the shelf cloud, and that's what's causing all that blowing dust there. So straight line winds. There are different kinds of tornadoes. What's called multi-vortex tornadoes. I'm sure you've heard about these in the news, or at least some of you have. They're basically when you have multiple mini vortexes rotating about each other. These are more common with bigger tornadoes. Sometimes in very strong tornadoes, you'll see multi-vortex activity. Basically, it's just multiple funnels or multiple vortices rapidly spinning. We sometimes call them sub-vortices or suction vortices, and they're not always visible. The suction vortices, they can add 100 plus miles an hour to the ground relative wind, so your most intense damage will be in these little sub-vortices. But keep in mind the whole kit and caboodle is only maybe 100 yards or 200 yards wide. We're not talking a mile wide thing here. We're talking very small vortices. Each of the sub-vortices is probably only 20 to 50 yards at most. And these sub-vortices can cause narrow arcs of extreme damage. And when I say extreme damage, I mean, EF 3, 4 damage, and right next to weak damage. So sometimes tornado surveys can be very interesting because you'll have pockets of extreme damage right next to pockets of very little damage. And it's because of these sub-vortices that are rotating through the larger vortex. Sub-vortices usually occur in groups of 2 to 5 at one time. Usually each sub-vortice lasts less than a minute each. So the larger tornado is lasting much longer and it's much more broad scale, whereas the sub-vortices, they come and go, there's not much organization to them, but they may be very frequent. Satellite tornadoes are basically, they're similar to sub-vortices. I guess you'd call it like a little sister tornado. These sometimes happen, and again, these are mostly with big tornadoes. You wouldn't see a satellite tornado with an EF0 or EF1. Usually these are with long-lived, stronger tornadoes. They develop independently from the primary tornado, so we're not talking sub-vortex or sub-vortex. We're talking full separate tornado, but it's in very close proximity to the main tornado.
Was that like the ones in Pilger?
Is it like what one?
The ones in Pilger last year?
Yeah.
And where?
Yeah, there was a satellite tornado with that one. The one he's talking about from last year, the Pilger, I think it was Pilger, Nebraska?
Yeah, I'm not familiar with that.
Yeah, that was when they had the double.
Okay. Well, we'll show you an example of one in our area near Evansville that happened back in '05. But anyway, these tornadoes, the satellite tornadoes, they're separate and distinct. The satellite tornado is kind of orbiting around the main tornado within the same mesocyclone. So that's why I call it like a sister tornado. It's coming from the same parent circulation. You know what I mean? The cause of these things is not known. There's a lot that we don't know about tornadoes. But like I said, they seem to form near the large and more intense tornadoes, like the Evansville tornado in '05, which was an EF3. Now, circulations you can actually have you can have a tornado, technically a tornado, not associated with a supercell. So far in this talk, we've been talking all about supercells. Well, you may someday you may see a tornado, but it's not associated with a supercell. The term for that is called a landspout. A landspout is a weak tornado. You will see a narrow rope-like funnel that forms when the storm cloud is still growing, and the spinning motion originates near the ground, so it's forming from the ground up. These are technically considered tornadoes, but they may develop out of very weak thunderstorms or even rain showers. You may not even hear any thunder with it. These are rotating columns there. They are in contact with both the surface of the ground and the cloud. What seems to cause the formation of these is some kind of pre-existing boundary. It could be anything really. It could be the difference between farm field and forest. Sometimes that causes a temperature contrast. We're not talking a front when we say boundary. It's a very small scale boundary. And then that horizontal boundary gets tilted upward by a developing updraft. It happens with very intense updrafts. Those are usually stationary, they don't move very much, and they are in a weak wind shear environment, so they don't fit the model of what we've been talking about here. In fact, more than likely they will not show up on radar. The damage of these is EF2 or less. And I'd say EF2 would be very, very rare. It usually would be a 0 or 1. And what drives these things seems to be the instability. They form almost like dust devils when you have a very hot, sun-baked ground. There'll be a very rapid temperature change with height. And so on days where you expect to see a dust devil, that's when conditions would be favorable for a landspout. But landspouts are very rare. And because they're so small and they are not associated with a larger scale circulation, the radar won't see them. It says very difficult to detect, but I don't know of one that's ever been detected by radar. They're very shallow, and like I said, the larger scale circulation is almost non-existent. It's just a very small scale circulation. But these are pictures of landspouts in New Madrid County, Missouri from April of 2012. And it looks like a really bad tornado. I mean, there's, especially the upper right photo, it looks like a pretty dangerous beast. But there was very little, if any, damage associated. Of course, they were in open farm fields, but the wind speeds are typically less than usually EF0, sometimes EF1, and possibly EF2 in extreme cases, but they're generally not going to cause structural destruction. All right, circulations formed without a rotating updraft. You can actually have what appears to be a tornado without an updraft, and that is called a gustnado. A gustnado is a short-lived, usually doesn't last long at all, ground-based, shallow vortex that develops along a gust front, basically along the shelf where the shelf cloud is. That's the leading edge of the downdraft air. It has nothing, it looks like a tornado, but it's mechanically completely different from a tornado, or even a landspout. It's associated more or less with the downdraft part of the storm, which makes no sense. But the reason it develops is because it's forming along that boundary. The gust front boundary is what causes it to form. It's not associated with an updraft or cloud rotation, and it is not connected to the cloud base. That's why it's not a tornado, because it's not connected to the cloud base. They may extend anywhere from just a couple hundred feet above the ground up to a mile or so above the ground, but they do not connect to the cloud base above, thunderstorm cloud base. And the best thing I can compare them to is a dust devil. They are not dust devils, but they are, a dust devil is not connected to a cloud, and it is a ground-based circulation, so that's kind of what you could compare it to. They may be accompanied by rain. Usually they look wispy or only visible as a debris cloud at or near the ground. Wind speeds are damaging. I mean, they're not, this isn't to say that they won't cause any damage. 60 to 80 mile per hour winds, that's enough to down or uproot trees. It's similar to an EF0 tornado. So the effects on you would be the same as a weak tornado. They often form with squall lines and bow echoes. They're associated with the gust front. And these also are basically non-detectable on radar. And again, the reason for that is they're so shallow. The radar beam is nowhere near that low to the ground to be able to detect a gustnado. If they're only a couple hundred feet off the ground, the radar is not even going to come close to picking it up. And also they're so brief, the radar probably wouldn't see it in any given volume scheme. Gustnados are also small, so that's another reason the radar couldn't pick it up. It's typically they're 20 to 50 yards wide, and there's not a parent circulation of the cloud. And again, if the radar, you have to keep in mind the radar beam is up in the clouds. So if there's no circulation in the clouds, then the radar is not going to show up the circulation. It's not that close to the ground. And that's why we need spotters to see these things, because radar is just not going to show anything that's that low to the ground. But here's this diagram basically shows the mechanics of how gustnados form. Basically, a downdraft hits the ground and it kind of splits into eddies, just like you see eddies when water passes up by the pillar. As it passes by the pillar, it starts in small. So here's a couple gustnados here, and again, they're not connected to the cloud base. They almost look like dust devils, and that's basically like a dust devil. They don't reach the cloud. Well, dust devils don't form on cloudy days anyway, but they're not connected to the cloud base. That's probably the main thing to understand, and also to understand that they're associated with the gust front. They're not associated with the updraft. Here's a relatively bad-looking gustnado. Again, not connected to the cloud base, and it's more associated with the shelf cloud. There's no wall cloud above that, and odds are it's going to be a brief type of event. They typically don't last more than a few minutes. But again, they can cause some minor damage, such as they can bring trees down, but they're not going to cause a total destruction of a house. All right, switching gears a little bit to mobile storm spotting safety, and I know that a lot of you don't engage in mobile storm spotting, and that's fine because it's very dangerous, and it's not something that we are encouraging you to do. It's more for people who choose to do this on their own, and or for people who are out in the storms, and whether they're spotting or not. If you get caught in storms, there's certain safety tips in here that the final, whether you're mobile or not, is safety. Always remember that we would rather not receive a report than put someone's life in danger. So we're not ever asking you to compromise your safety in order to give information about a storm. That's not at all what we want you to do. Safety is always the bottom line for anybody. So whenever you're outside, always ask yourself how much danger you're in. Evaluate every situation for potential safety concerns. The number one threat when you're driving in storms is driving. Spotters are prone to all the hazards associated with driving. And part of the problem is you're distracted. You're distracted even in good weather, but when there's storms going on, you're going to have more distractions. You're going to be distracted by the storm itself. You're possibly more prone to driving above the speed limit, especially if you're trying to chase the storm, which is not recommended. Driving down rain or hail-covered roads is a very big hazard. And even in a normal rainstorm, that's dangerous. You're going to possibly be tempted to make sudden stops and starts without warning if you're trying to observe a funnel cloud or tornado. You may want to catch up to it, or you may want to stop to get a picture. Those are both dangerous things to do. Driving in adverse conditions like low visibility due to rain or hail, the pavement's going to be wet, so your traction's going to be worse. You're going to have gusty winds. That's going to tend to affect the handling of the vehicle. And then, of course, you've got your gadgets. You've got your GPS, you've got your cell phone or your PDA, you've got your camera. All these things add up to a very dangerous situation. So basically, you are your biggest hazard when you're driving, doing mobile spotting. So the best thing to do is not go out alone. Have one person dedicated to the driving, and have the other person do the spotting, have the other person get the gadgets out, and take all the information down. But you got to have a driver dedicated to the driving. And remember, even if you're the best driver in the world, you're going to have issues if you're driving in rain and hail and wind, because that's dangerous under the best conditions. Always be careful when you're driving on water-covered roadways. You've got hydroplaning, that's a serious threat. You're going to have water collecting on the tire paths. Even a well-drained road is going to have basically puddles where the tire, where the grooves are in the pavement. Be especially cautious at night. It's very hard to see water over the road at night. Just be extremely aware of your winds, your storm behavior, and potential for large hail and tornadoes. Again, if you hear splashing sounds, you're on the verge of hydroplaning. And of course, use your headlights in the rain. That's something that a lot of people forget to do. And don't speed, especially when the roads are wet. Now, parking is another dangerous thing to do when you're on the go. You don't want to stop in the middle of the road. Obviously, you don't want to park halfway on the road and off the road. When you pull off the side of the road, make sure that you're far enough off that you're not even close to being in anyone's way. Don't park in an illegal spot. Don't park in someone's front yard. When you're opening your door, remember that your door is going to extend out toward traffic, so make sure you're on the road enough, off the road enough so that you can open it. These are common sense things, but when you're all excited about chasing a storm, you can forget about all this. And I know I've actually, it's happened to me. I was observing a severe storm that was tornadic, and I disobeyed a bunch of these things. And that's why I never do it again. I don't chase storms. So the best thing to do is go with someone else who can concentrate on the driving. And when you do pull off the road, check the shoulder, make sure it's in good condition. You don't want to get stuck in the mud. And if you're on the interstate, be especially careful. You're not supposed to pull over on the interstate unless it's an emergency. And always have your parking lights on as well. And once you stop and you're looking at the weather, it's probably a good idea to have your engine running and your doors open if you need to make a very quick escape. Okay, spotter vehicle. Whatever you're spotting in, make sure that it's in good condition. Make sure the tires are at the proper tire pressure. Make sure that you got a spare. Make sure your wiper blade's in good shape. It's always good to have one of those little road emergency kits that have the flares in them. Tire jack is good to have, road flares, jumper cables. You don't want to get stuck anywhere where you could possibly be in jeopardy. Make sure your windshield's clean. If you have Rain-X, that's a great help. That really helps keep your windshield nice and clear. Make sure all your lights work. These are things you probably should do anyway. Make sure your gas tank is full. You don't want to get stuck out in the country in the middle of nowhere, which a lot of times when you're chasing a storm, you'll end up in the middle of the country because that's where you have your best views at. And you can forget that you can forget to look at your gas gauge if you're actively following a storm and find yourself on an eighth of a tank and you're about 20 miles from the nearest village. And then use your turn signal. Again, common sense things that you can forget about when you're in the heat of the battle. Okay, that was the number one threat for driving. That covers a whole bunch of stuff. Now the number two threat is lightning. Because of the fact that you are trying to be near a storm or observing a storm, you are going to be inherently prone to being struck by lightning. You're going to be around thunderstorms a lot. You're going to flock to the high spots to get a good view, and of course lightning tends to strike the high spot. You're going to have fences and power lines and phone lines in the area. You're basically, because you're not in your house, you're just going to be in a more vulnerable position. You're going to, if you're using cameras or CB radios, those things are hazards with lightning. And almost all fatalities have occurred while the victim is outdoors. So remember that although your spotting vehicle is not a safe place in a lot of situations like tornadoes, it is a safe place in lightning. That's the one thing a vehicle is definitely a safer place to be in is when you have lightning. You may not think that. You may think, oh my gosh, there's lightning striking real close by. But if you're in your car, you're safe. Unless it's a convertible one. I wouldn't recommend a convertible as your spotting vehicle. Keep in mind, though, the Weather Service does not issue warnings. It doesn't matter if the lightning is continuous. It doesn't matter if it's the worst lightning storm ever. That does not make a storm severe. We may put in our statements and warnings that this storm has a ton of lightning, but we're not going to issue a warning just based on the amount of lightning that's in it. And lightning is one of the most deadly things, so remember, if a storm does not have a warning, that doesn't mean that it's not deadly, because lightning is deadly.
Seriously, this is probably stupid. I'm probably gonna kill myself. Oh man. Something to like right now. Oh dear. Alright, if I die, tell my family after. We just got hit.
Okay, that was Beavis and Butthead almost getting struck by lightning. So the number one threat that we covered was number two threat was the lightning. Number three, believe it or not, is the storm itself. That's probably less of a threat than the other two things. Spotters unfamiliar with severe storms, that would be people who haven't done this or seldom do it or don't do it for a living. You simply may not be able to comprehend the danger until it's too late. Smart spotters never take risks near severe storms. You always should comprehend what's around you and know when you're in danger. And if you're in danger, you should know what you can do to prevent being hurt. Severe storms can become unbelievably fierce really fast. They can, move at 60, 70 miles per hour, so you don't have all day to react. You have to anticipate, keep a close eye on what's going on, and not wait until you're in the middle of extreme danger. Even non-tornadic storms can have winds of 70 to 100 miles per hour. And if you've got hail mixed in with that, that wind-driven hail will destroy everything. If supercells often bring, the HP supercells, high precipitation supercells, often bring very vicious weather. So even if a storm is not tornadic, if you're with an HP supercell, you've got a lot of hazards, a lot of wind, a lot of hail. You don't want to assume that just because there's not a tornado or tornado warning that this is not a very destructive storm. Minimize your risk. The best way to do that is to not core punch. In other words, don't go through the heavy rain and the hail and the downdraft area of the storm to get to the hook echo. In other words, don't try to get to the tornado from north or northeast. by going through all the heavy rain and hail. That's just a dangerous thing to do. The driving conditions will be terrible. The large hail, for one thing, can totally mess up your car, and it could even break your windshield. And then, of course, you've got to worry about the factor in driving down rain. You could have flooding. The roads are going to be very slick with the rain. And so if you're driving in the vicinity of a supercell and you find yourself encountering hail that's increasing in size, those bad data points, but not all. So there's some bad data that comes out of that radar, and if you don't know what you're looking at, you can seriously make some incorrect judgments. Many of you have heard of the cone of silence. That simply refers to the cone directly above the radar that the radar cannot see. It can't see anything right above itself because it doesn't go into the vertical. It's always scanning in circles at an angle, but it's never tilted more than about 15 degrees above the horizontal. So you're not going to see what's going on directly above it. So whenever we have a storm right over the Paducah airport, we can't use our own radar. We have to look at Fort Campbell's radar or Evansville's radar, which actually is close enough that it gives us a very good idea what's going on. So here's what a cross-section looks like. This would be a cross-section showing the distance from the radar and the height above the radar. And directly above it, there's not going to be any data, and that's because the radar beam is not pointing that high up above the radar. Okay, another limitation with radar, anomalous propagation. Don't be afraid of those big words. All that means basically is false echoes. And a lot of times, what you're looking at there on the left picture in reflectivity, some of those echoes are real. That's a real thunderstorm to the northeast of the radar. But all this stuff down here is just false returns. And the only way you would know that is, well, it helps a lot to have a lot of experience looking at it. But when I look at it, I see that mottled appearance. It's kind of just a mottled appearance is the best way to describe it. But another key giveaway is that when you animate it, it doesn't move. False echoes seldom move. That's the biggest giveaway. In these pictures, you can see the storm in the upper right-hand corner, along with the large area of blue near the center of the picture. The blue near the center is the radar site itself is right in the middle. This is the radar. You got the thunderstorm northeast and the false echo southwest. In the base velocity, there's near zero velocity in those false echoes. That's because they're false echoes. They're not. If they were real targets, they would have some movement. In the thunderstorm, at least you've got some movement. You don't have zero velocities in the thunderstorm. Okay, then another limitation is called radar sampling. We talked about the cone of silence. The radar can't see directly above itself. Aspect ratio, that refers to the widening of the radar beam. The further the beam gets from the radar, the wider it gets. So if you have a small target far from the radar, it's not going to sample the whole target. It's only going to give a partial picture. And then another issue is if you have a very big target right next to the radar, the beam is too narrow to sample it correctly. And then radar horizon in the lower left, that just refers to the fact that the radar beam is getting higher above the ground as you get further from the radar. That's because there's curvature to the earth. So even if the radar beam was perfectly horizontal, it would still be above the earth because the earth is curving down away from it. And then viewing angle is another thing. The same storm can look different on two different radars because the radar beam is intersecting the storm at different levels, and it's also at different distances from the radar. So Paducah's radar may show something different than Evansville's radar when you're looking at the same storm. It depends on how close the radar is to the storm. Okay, how do we determine these things from the 88D? And it's called the 88D because it was built in 1988. It's actually kind of outdated technology, or at least Well, I shouldn't say that. We have the dual polarization add-on, so it has been modified to incorporate the latest technology, but but the hardware is basically from 1988. The radar sends out numerous pulses of energy. When this energy hits the target, some of it is reflected back to the radar. And the way that the computers determine the distance of the storm is they time how long it takes for those pulses of energy to get back to the radar. Pretty simple concept, and it's been around since World War II. The intensity of the storm, or the intensity of the rainfall or hail, is determined by the amount of energy that the radar gets back. If it's a very intense target, then all of that energy is going to be reflected back to the radar. If it's a weak target, some of that energy is going to go through the target, and you only get a little bit of energy back to the radar. The radar can estimate rainfall amounts. It doesn't measure the rainfall, but I'm sure a lot of you know that you can look at storm total precipitation. The radar is actually estimating precipitation amounts. It does that by basically taking the power returned back from the echo, and then it kind of estimates the rainfall rate based on the strength of the reflectivity. So if it's a very intense rainfall, the radar will get a lot of power back, and it will say, wow, it's raining really hard in that spot. And then all that information is fed through a series of equations that the computers have algorithms for, and then it comes up with a precipitation estimate, and so we're able to tell approximately how much rain has fallen in a certain amount of time based on the radar. So here's an example of the storm total rainfall for April. This is April 26, 2011. This was one of our wettest, well, this was one of our biggest rainfall events on record. The dark blues, the aqua blues and greens in southeast Missouri, those represent over 10 inches of rain. It was 10 to 12 inches of rain in the Cape Girardeau area. This is when we had the Ohio River nearly flooded Caro, and they had to blow up the levee at Bird's Point. This was like the final straw that caused the Ohio made them have to blow the levee up. And it was our wettest month on record. Not just our wettest April, but our wettest month on record at Paducah. Okay, I mentioned briefly dual pol products. The radar has a new add-on. Dual polarization is what it's called. Real fancy schmancy stuff that we really haven't had much experience with yet because we've only had it for a couple of years. But it does some really nice things that tell us a lot of information about storms and about precipitation types. Three things that you can look at that might be helpful to you. One is called correlation coefficient, or we call that CC. Basically, it gives information about the uniformity of the targets. In other words, are they all different shapes and sizes or not? Another thing is differential reflectivity that tells us about the shape of the particle. And another third thing is differential reflectivity tells us the concentration. And by telling the size and shape of the particle tells us a lot about the type of precipitation. It's great in the winter. It tells the difference between sleet and snow, or between snow and rain, or mixed precipitation. Only problem is the radar beam's way above the ground, so we still don't know what it's doing at the ground. But it's very helpful to know what it's doing even 5,000 feet above the ground. And another great thing about it is it can because we know these things about the targets, we can tell when there's a tornado. One of the great things about it for severe weather is it's great at detecting debris in the air. And the correlation coefficient in particular tells us whether or not there's debris from a tornado lofted up. And that's been one of the most useful things so far about dual pol, is the ability to detect tornadic debris columns, which we're finding out that tornado debris gets lofted as much as 20,000 feet into the atmosphere, and the radar can tell that. That's pretty amazing.